Okay, I'm back, and now we want to talk about Newton's second law of motion. But before we do that, I want you to go to this simulation here. So you're going to go to PHET, P-H-E-T, and then Forces and Motion Basics, and find this simulation. Okay, have you done it? Okay. So now we're going to click on Net Force, and what we have here is a cart, and we're going to be pulling on that cart with various amounts of force. So remember, a force is a push or a pull. So let's take one of these little guys here, and this guy is going to apply a force to the cart, and then let's see what happens. So we're going to hit the go button. Okay, and you see that the cart begins to move. All right, so let's reset it. And so immediately we can come to a conclusion that if the force F is in that direction, then the motion of the cart is going to be in that direction. Now at this point, we can't really say what the motion is, but we can say that the cart moved in whatever direction the force was being applied. So let's try it again, but this time let's have a little guy on that side, and let's put a little guy on this side. And now I want you to make a prediction before you hit the go button. What do you think is going to happen? Okay, and then hit the go button, and nothing. Okay, so you had one person that was pulling in that direction, you had another person that was pulling in this direction. They had equal and opposite forces. So do you remember what the sign convention was? So if a force is going in this direction, we would say that it has a negative force. And then if we add it to a positive force that's going in the other direction, then you notice that these cancel out, and then you would end up with zero net force. So what I wanted you to get out of this is it takes a net force in order to be able to move something. So there was a lot of force being exerted in this picture, but the problem was it was all canceling out, so that the net force was equal to zero. Okay, and so now we could reset it, and this time if we put a big guy on this side, can you imagine what's going to happen? All right, and then hit the go button. All right, and you notice that it starts to go to the left again because there is a net force in that direction, so the motion is in that direction. Okay, so that's what I wanted you to get out of this. Okay, and so let's get out of this one, and then let's go to this one here. Okay, so this is the one that says motion. So I clicked on this one, and now we've got a cart here that you can push on. And so when you take this slider down here and you move the slider, you can apply a force. So you can apply a force in this direction, so that's a positive force, and so again we can hit the reset button, which is up here, and we could also apply a force in that direction. So again, notice that whatever the direction of the force, that's going to be the direction that the object is going to move in. But remember that I wanted to come up with a description of the motion. So how would we describe that motion? So we're going to hit the reset button again here, and what we can do is if we click on these various boxes, we can put numbers on everything. But the most important thing is this speedometer, this thing right here. So I want you to observe what happens to the speedometer when I apply a force. So I'm going to apply a force to the box, and I'm going to apply the force in this direction. And I'm going to apply, well, it looks like 74 newtons. So 74 newtons of force. What is the speedometer doing? Okay, now I'm going to stop applying the force, and now observe what the speedometer is doing. All right, so based on those observations, so now we can reset it again, and let's take a look at what does this mean. Okay, so how would you have described the motion if the speed was changing? That was called a acceleration. So what we've just figured out is when you apply a force, an object is going to accelerate. Now I'm going to give you two different versions of the quote-unquote formula. So I'm going to say that A, is it proportional to the force, or is A proportional to 1 over the force? So you have to figure out which of those two is correct. Now how would we do this? Okay, so go back to the simulation. Let's put the speedometer on there. And what I want you to do is do 2 trials. So do trial number 1 with a small amount of force, and then do trial number 2 with a large amount of force, and then observe how does the speedometer change. Okay, so go ahead and do that. I'll wait. Okay, did you do it? Okay, so let's do it with a small amount of force. So it looks like that's what? I'll let you read that number. 110 newtons. Okay, you see what the speedometer is doing? Okay, now let's repeat the experiment. Okay, put the clock back up there. And now let's do it with a lot of force. Okay, did you notice something about the clock? So that when you applied a lot of force, the clock sped up faster. So what does that mean? More acceleration. So what we have just shown is that a small amount of force is going to produce a small amount of acceleration, and that a large amount of force is going to produce a large acceleration. Now that we know this, which of these two is the correct one? So this one would say, since it's directly proportional, if you increase the F, you increase the A. Is that what we saw? Yes. We increase the F, it increases the A. Okay, what would this one be saying? All right, so this one would be saying that if you increase the F, it's in the bottom part of the fraction. So like 1 divided by 10 is 0.1. So this number would get smaller, and that did not happen. So now what we know is that the acceleration of an object is proportional to its force. Now at this point we don't really know whether maybe this thing should be F squared or maybe this thing should be the square root of F. We don't know that. But we do know that if F gets bigger, then A gets bigger. And so we're going to put it like this for the moment, and then eventually we're going to figure out what that is. Okay, so let's go ahead and reset it. And now we want to change the parameters of it, and this time we're going to change the mass. So you notice that what we've got here is a box, and then if we turn on these things here, you see that it tells you what the mass of this thing is. Okay, so now we're going to get rid of the box, and instead we're going to use the refrigerator. So that refrigerator has more mass. Okay, so let's go ahead and push on it. And now what we want to try to do is use the same amount of force each time. Okay, so that if we apply a certain amount of force to this refrigerator, okay, now what you could do is look at that stopwatch there and look at what's happening to it. So we're not really making any measurements yet, we're just observing. Alright, now let's reset it. Okay, and now let's repeat it. So we're going to use the same amount of force, but notice that we're using the smaller mass. And let's see what happens. So I'm using about the same amount of force that I did before. Oops, sorry, reset it. Need a clock. Alright, so there's my clock. Alright, let's try it again. Okay, do you notice anything different? The speedometer is going up faster than what it did before. So you could actually do this with a stopwatch, and you could see that the speed was getting faster quicker. So that means the box has more acceleration. So let's write this then and say, is the acceleration, is it going to be proportional to m, or is it going to be proportional to 1 over m? So again, which of these two makes more sense? So based on what you saw with the simulation, what conclusion do you come to? Okay, when you use the refrigerator, it was a larger mass. So what you saw was that if you used a large mass, it was the refrigerator, the clock did not go up as fast as it did with the crate. So it meant that the larger the mass, the smaller the acceleration. And then when you use the crate, so the crate was the one that had the small m, you should have noticed that it accelerated more. So the speedometer went up faster. So it'd be a big A. So this is what we just figured out. And so which of these two mimics that? So the first one here would say, if you increase the m, it would increase the A. But that's not what we saw. So what we saw was that if you increase the m, it decreased the A. So that means that this one here is not correct. And so now we know that the acceleration A is also proportional to 1 over m. Okay, we're making progress. You may not think so, but we're making some progress here. So now what we want to do is take these two proportions and then put them together. So if we take those two proportions and put them together, what do you get? So we want to say A equals. And so if we know the m has to be on the bottom, and we know the f has to be on the top. So if you look at this, you see that both of these two proportions are inside of that one equation. And now if I take the m over to this side over here, then I end up with force is equal to ma. Dun, da, da, da. There it is. So that is Newton's second law of motion. A force causes a mass to accelerate. Got it? All right, let's take a break. When we come back, we will show how to actually use this in word problems.